homework number 10 in dynamics. We got problem number 1. So we have the aerospace program has made a spacecraft that has a mass of 600 kilograms. And when we're starting out right now, it has a velocity of 35 meters per second, traveling at 20 degrees. Now remember, this is particle kinetics. So this thing is not going to rotate. We don't care about the rotation of the thing, but it does have some orientation, okay? So that's maybe a fine point right there. And in the beginning, its orientation is aligned with what direction it's going, right? Now the thrusters have a strange property in which they actually behave, they change the amount of thrust with time. So as soon as you engage them, there's an immediate amount of thrust, but then it starts to increase, right? So the front and rear thrusters behave like A plus B times T, right there, right? So it's this guy right there, that equation right there. It's a function of time. I've graphed it out over here, what that looks like. And then the thrusters in the starboard and the port ones, they have a slightly different thrust profile, a thrust versus time profile. And so they look like C plus D, where the A and B are 20 and 40, and the C and D are 15 and 20. And we want to find out, we want to determine the velocity vector, magnitude direction, when the rear and the starboard thrusters are engaged for 20 seconds. Okay, so starboard means to the right, and port is to the left. If you want to use something to help you remember that, port is 4 letters, and so does left, right? So you could go port is left. There you go. Probably there's other mnemonics and that kind of thing. But that's, on ships and on airplanes, we have starboard and port, starboard. So you should learn that if you don't know it already. Anyway, we want to find the velocity vector after these thrusters have gone on for 20 seconds. And we also want to find the average force vector. So let's get to it. All right, so I've written out like a summary of my work right here. And I did this problem with like a preliminary type of thing just to check that the numbers made sense. Okay, so in our impulse and momentum problems, we want to definitely use a diagram to try to keep things straight. So this one might be kind of a little bit of a simple one. But anyway, what we're going to do is we're going to draw this thing in its initial velocity, right? So I might put these things in here into place. And I can't remember do I write initial? I guess I write initial. I'm going to write initial. Leave this in, and then I'll write impulse. Let me see. I should try to fit that in there. I like to make it horizontal. I'm just gonna kind of budge it a little bit. Impulse. Spell impulse correctly. That'd be helpful. Impulse, and then I'll go after. No, I'll go final. Right. So there's, yeah, I'm going to start all over. I want to make this neat. Neat work needs to neat thought, right? No, organized work leads to organized thought. That's the way it goes. So we're going to have initial. We're going to have impulse. And then we're going to have final. So we're going to draw 3 diagrams. Right. And I'm going to go ahead and break this thing down, right? So here's going to be my coordinate axes. I'm going to use X and Y and I and J going on here. So we're going to have some initial M times V1 in the X direction, M times V1 in the Y direction. Now the impulses are going to be happening onto this thing. We've got to be careful here. They're happening kind of like that right there and that right there, where we're going to have an impulse happening right here and an impulse happening right there. Now this right here is theta, and this right here is theta, right there, right? Just by the way the orientation of the original problem. Take a look at it. You can see that here's the horizontal right there, and you can see we're making an angle of 20 degrees right here. So that's why that's arranged there. And let's write it f dt. Right, and maybe I'll write this as the rear one, and this is f, and this is the starboard one, dt. So these are the impulses that are taking place onto this. And then we're going to find a final, and I'm going to assume that these are both in direction. So we have the mass times velocity 2 in the y direction, and mass times velocity 2 in the x direction. And the reason why I chose this problem was I wanted to make sure that we kept in mind that the main equation that we're going to use is made up of as a vector, right? So let's see, mv1 summation of all the initial state 1 impulses plus. Let me see, 1 second. Let me take a look at my equation sheet. I want to definitely try to tie this to our equation sheet. So let's take a look at that. And so right here is our impulse and momentum right here. Okay, so maybe I want to write this out first, just so that so I was about to write this out, but maybe I'm going to write this out in our first homework solution so that we can really start to tie the problems to our equation sheets and to the big concepts and things. All right, so this is going to be L1, and you notice a vector plus, and I go IMP from 1 to 2, states 1 to 2, and that's a vector, is going to be equal to L2. All right, so this is linear momentum. That's why I decided with a capital L as a vector. All right, and then so writing that out, that's MV1. It's the summation of all of the momentums, and notice it's a vector, plus the integral from time 1 to time 2 of f is a vector, dt, not a vector, is going to be equal to the summation of all the momentums afterwards. Okay, now from here, we want to try to write it. I might do like a little bit of stuff in the initial. Just because it might make it easier to write this out. I'm trying to decide. Sure. Yeah, because we have the nature of this thing, right? That we have. Two separate graphs. Oh no, I wrote them. I do the graphs up there already. Or want something to represent the graph. I need to integrate this. That's what's going to happen. This is a function of time, and I need to integrate that, which is to say I need to get the area underneath it. But let's go ahead and integrate the forces, right? So to get the impulses. So how do I write this out right here? I'm going to go like impulse magnitude, maybe. I'm going to go to impulse magnitude of the rear one. It's going to be equal to the integral from 0 to t of my 20, I'll put a bracket there, 20 plus 40 t dt, right? So and that's going to be, well, let me put out, go ahead, I'll put as 20 seconds. There's no reason to get this in any other terms. So we got 20 t plus 1/2 40 t squared from 0 to 20. And if I plug 20 seconds in there, and of course the 0 is just going to go away right in there, I believe I'm going to get 240. No, I'm going to get 8,400. 8,400 400. All right, so here's the magnitude of the impulse right here. So, and I think maybe I'm going to stick with writing it this guy right here. I'm going to write that guy out here. So I'm going to go the impulse right here, F from T1 to T2, and this is the rear dt. Okay. And these are going to be in units of Newton seconds. And then I'm going to go from T1 to T2 of my starboard dt, integrating from 0 to 20 in brackets, and say that it's 15 and 30 t dt. That's going to be equal to 15t plus 1/2 30t squared, going from 0 to 20. And I believe that I got, what did I get? 6,700 Newton seconds. And let's see if I could say this the right way. I decided not to make it the absolute value, so this should be a vector, and it should be coming off that way right there at 20 degrees. And this one right here, we should be going up here at 70 degrees, right? Because he is, in fact, I might actually prefer, because the way that I wrote this, I usually want it referencing the horizontal, but the way that I drew it right here, I'm going to, let's see, I'm going to say, I'm drawing a blank. I'm going to go draw that way, right there, right? So that's going to be 20 degrees that way. So it's coming 20 degrees from vertical that way. All right, so now I'm coming back over to here, so I'm going to continue. That was just writing this part out right there to make it easier. So here, remember the thing is starting out at 35 meters per second and 20 right here. So we're going to say in the x direction, this is the way I like to do it. I like to go x. So I wrote this out generally here, and then I'll write this out in the x direction. I'll go m v1 cosine of theta plus integral FR dt, right, from T1 to T2, and say that that's going to be times the, in this case, that's the cosine of theta, right, because that's the angle right in there. And then, but here, you're going to see that it's going to be in the negative direction, right? That the x direction of this is negative. So we're going to say minus T1, T2, F, here's the starboard one, dt, and the sine of theta. And that's going to be equal to mass times velocity 2 in the x direction. Here, I don't know what but this will get me just the x direction right here, which is going to be a good thing for us in terms of answering as a vector. So we'll just say that it's going to be 600 kilograms times 35 meters per second times the cosine of 20 degrees plus 8,400 times the cosine, also 20 degrees. And that's because of the orientation of the thing starting out. Okay, so remember, it's not gonna rotate. It's a particle still, but the forces that we're talking about are aligned with this direction. That's why we're doing it this way. And then we have minus 6,700 times the sine of 20 degrees. It's going to be equal to 600 times V2x. So I'm going to get V2 V2 in the x direction, if I did this correctly, I'm not 100% sure I did, but that's okay. I think I get 42.23. And this is meters per second. Now I'm going to do the same thing for the y direction. And I'm almost kind of tempted to not write out the this part of it here just to put the numbers in, but I'll go ahead and put these in here. mv1 sine of theta plus, and we're going to have to squeeze in here, t1, t2, integral fr dt. Now it's going to be the sine of theta. Now this is plus, right? Because this one is going in the positive direction. This one's going in the positive direction. This one's going in the positive direction. It was only negative for this one because it was going in the negative x direction right there. But once again, one of the reasons why I set up this problem that way was trying to make that vector emphasis as part of the problem here. And now we go cosine of theta equals mass times v2 in the y direction. It's supposed to be a y, it looks like a j or something. So we'll stick some values in here. 600 times 35 times the sine of 20 plus 8,400 times the sine of 20 minus 6,700 cosine of 20 equals 600 times v2y. And if I did the math correctly, v2y is going to be 27.25 meters per second. So let's see. I already have the tear off 2 pages. And continuing on from here, this is page 2. We'll fill out this later. We want to write out our result here as a vector is going to be 42.23 I plus 27.25 J meters per second. Let's figure out what our magnitude is going to be. 42.23 squared and 27.25 squared. And I think I get 50.26 meters per second. I'll have my theta 2 in terms of the traveling of the thing, inverse tangent of rise over run, or 27.25 divided by 42.23, and I end up with 32.83 degrees. So I can write that out at the end when I put out my answers. But that's the magnitude and direction. So remember, there was originally traveling at, wait a minute. Did I do this incorrectly? No. Originally it was at 35 meters per second. Now it's at 50, so it's increased, and it was going at a 20 degrees, but now it's going at 32 degrees, right? So it was coming this way and going that speed, but now it's kind of go this way and change that speed. But it didn't rotate because it's not a particle. So even though the thing looks like, hey, maybe it's spinning, it doesn't. It just has that orientation. Okay, and now we want to have the average force. So we actually have, we could do this in, I could do it in a number of ways, but I could find out, here's the total impulse that's happening in the x direction. So let me write this right here. Then in the x direction, the impulse is equal to, let's see if I do this right here, 8,400 times the cosine of 20 minus the 6,700 times the sine of 20. So I think we get, I think I get 5,602 Newton seconds. And therefore the F average in the x direction is going to be imp x over delta t. Right? So we're going to get the 5,602 divided by 20 seconds, and we end up getting 280.1 newtons. And then in the y direction, we'll say the impulse in the y direction is going to be 8,400 sine of 20 minus 6, plus. That's good. They're both positive. This is the only one that was negative, remember, because it was going that way. Cosine of 20. And if I did that right, I believe I get 9,169. These are Newton seconds. You can think of impulse as a thing. And then so we're going to have the average y is going to be equal to the impulse in the y divided by delta t, or 9,169 divided by 20. So we end up getting 458.5 newtons, right? So if we wanted to write this as a vector, the average force that we have here is going to be 280.1 I and 458.5 J, and these are newtons. But it'd be nice to have as, because we're going to give this answer a velocity in terms of a magnitude and direction. We have to do it also with the force. So 280.1 squared plus 458.5 squared, and I believe I get 537.3 newtons with a, I'm just going to call this theta F, and 458.5, 280.1, and you will get a 58.58 degrees. So we're done. We got the answers. A is going to be velocity after this impulse has been carried out of 50.3 meters per second. And put the quadrant in there, and we have, that's going to be at 32.8 degrees. And then B, we're going to have the average force is going to be 537 newtons, but it's taking place at 58.6 degrees. And my ruler disappeared. So I'll box them up. Ta-da, the end. How long is this video? 24.5 minutes.